Okay, we've got kind of a pretty picture here, but I don't want to talk in terms of that picture. We'll come back to it. I just want to talk in terms of the way we constructed that picture. We have a region that's defined by 0 less than or equal to x less than or equal to the square root of y, and 0 less than or equal to y less than or equal to 2. We want to depict that region. We want to see what that region looks like. So what I'm going to do is I'm going to pick a y value here, and I'm going to call that y1. And I'm not going to put a scale on this. I don't want a scale right now. I just want to get a feeling for the soul, so to speak, of this relationship. Okay, so y can be any number between 0 and 2, so we start with a value of y, and we ask what values of x would correspond to that. What points in the plane would correspond to this description for a given value of y? Well, for the given value of y, x can be as much as the square root of y. So this could be the square root of y1. So we would have a point on the graph. Okay? Now, I've got a y1 and a y2, and actually I want to go to a y3 and a y4. You'll see why in a minute. Now, I'm going to assume all these are equally spaced so that this y is 4 times as big as this y. Okay, well, if y is 4 times as big, then what can we say about the limits on x? Okay, well, the limit on x would be the square root of y4, which would be, okay, if y4 is 4 times y1, then what's the square root of y4? Well, the square root of something that's 4 times as big is twice as big. And that's the point of this idea that I'm going to double the value of the square root of y if y increases by a factor of 4. So I've got this y up here that's 4 times as big as this y, and I'm writing that now as 4y1. The square root of 4y1 is just double the value of y1, so that y is 4 times as big. The limit on x is only twice as big. Okay? Now let's just think about, well, then we can say when y1 equals 0, the limit on x is 0. Okay, when when we have y1, the limit on x is whatever the square root of that is, and when y1 equals 4 times that, the limit on x is twice as big. From these points, we can construct a curve that corresponds to x equals the square root of y. Furthermore, when y takes a given value, x can be anything from 0 up to that value. Okay, so if we fix y at y equals y1, possible x values run from 0 to the square root of y1. So the possible x values go from here to here. Okay, if I go to y value y4, the x values run from 0 to the square root of y4. y4 being 4 times y1 by our assumption. Then the x values can change from 0 to a value twice as great as this one. Similarly at y2 or y3, the x values go from 0 out to the square root of whatever that is. And this curve gives you the x equals square root of y. Now we can just kind of eliminate this labeling because we know how we did this, and those labels aren't really important. What does become important is that we know now that y is supposed to go from 0 to 2. Okay, well now we can go ahead and put 2 on our picture, y equals 2. And that's going to allow us to go out here to x equals the square root of y, which is the square root of 2. And when y equals 2, x goes from 0 up to the square root of y. That's from 0 to the square root of 2. Okay, well, for any y, x is going to go from here to here. Okay, so here's kind of a picture of this region. It would include these lines for all possible values of x. Now I'm not going to draw all possible values of x. It wouldn't take too long before the chalk width would just fill in the whole region. But now we understand that if y goes from 0 to 2 and x goes from 0 to the square root of y, this is the shape of the region we're going to get, that this picture reasonably represents the region. I can also, since I eliminated the labelings of y1 and y2 and everything, I can eliminate all that as well. Here's the picture. Now, of course, x equals square root of y is part of the curve y equals x squared. So we could equally well represent this in terms of vertical segments. Okay, for a given value of x, where does y start? Well, if x, wherever x is, here's a value of x, the region starts here and ends here. So the region corresponding to this value of x goes from here to here. Okay? Now we see that x will go from 0 to the square root of 2, so we could write this as 0 less than or equal to x less than or equal to the square root of 2. What are our limits on y? We see that y goes from some value to some value. What value goes here and what value goes here? Well, for given x, what's the smallest value of y that we're going to have? And what's the biggest value of y that we're going to have? You should answer that question before I answer it for you. Okay, well, hopefully you've done that. Well, if this is x, and this is the curve y equals x squared, then what is the y value here? Now you should be able to answer that if you didn't answer it before. But you see that, well, that value is going to be x squared. Okay, and if I have a value of x, what's the value of y here? Well, this region is cut off at y equals 2 by this definition. So that this region goes up as far as y equals 2, so right here is the same region. So, there are two ways to express this same region. If you're trying to express it in terms of fixed limits on y from here to here, then you're going to want to express x as a function of y, so that when you know y, you know how far to go before you how far this segment will go in the x direction. if you want to express it in terms of fixed limits on x, then you're going to do this sort of thing. You're going to use y as a function of x. Okay, you're going to turn this around to this, and that's going to tell you the minimum and maximum values of y in terms of x. And then, of course, we do that for all possible values of x, and we get a bunch of segments that look like this, and they're supposed to be equally spaced, before they sure weren't. Okay? And the purple corresponds to this description. X takes values from 0 to square root of 2, and y then goes from x squared up to 2.